recording. All right, welcome everyone. Let me go ahead and cover some addition that we have for the class as far as home-based test equipment. So the department had ordered these units at the beginning of the semester, and it looks like we just received them. And I spoke with the department chair about implementing it in this class, and so we both discussed that and wanted to use it in this class. So here's kind of what it is. Okay, it's a USB type device. You plug this into your computer, and then on the side here you have these connectors that you can put wires into. Now there is a two-channel based oscilloscope. An oscilloscope plots voltage with respect to time. And I've been showing and doing video casting of my oscilloscope, so you guys have all seen that. How we can use an oscilloscope to view the waveform and see the voltage change with respect to time. So this device over here basically connects to your USB. You run some software. The software looks a bit like this to some degree, and allows us to view waveforms. Okay, so this is going to act like our oscilloscope. Also, it will act as a function generator. So I've been using a function generator to apply a stimulus to our circuits under test. So this has the ability to not only view the signal, but to produce signals. Okay, so those two fundamental things will allow us to apply a function to our circuit under test, and then to view the output as well as the input at the same time. Okay, so we're gonna go ahead and use this for the remaining labs of this class. Now, how do we go ahead and get this? So the unit itself is $200, and you don't have to buy it. The department has ordered them, and they will loan them out so that everyone can borrow it and then return it at the end of the semester. Now, what that means is there's going to be an agreement for loaning and checking out these. Now, if you go to my website and click on the 311 page, and you go to the lab equipment borrow section, I just added this. There is a file here. Download this file, fill it out, change the file name to reflect your name, and submit on Beachboard Dropbox. Okay, I already opened up a Dropbox for it. The Dropbox is listed as equipment loan agreement. So you're going to download this document file. And when you open up that document file, you'll see it's been partially filled out by me. Okay, so it's for the CECS department. It goes over the borrower responsibility. So when you fill this out, you are agreeing to arrange and return the equipment to the department. Campus drop off or shipping via mail. Now, where will you get this from? The bookstore. The bookstore on campus has agreed to hold these units for us and then loan them out. But you're going to need permission to receive this from the bookstore. So that's where this loan agreement comes into play. So I'm going to collect these loan agreements from everyone. Hence, there's a Beachboard Dropbox. So you download this file, you fill it out, you submit it on Beachboard Dropbox. I will collect them. We will serialize the units. So the units will have a serial number attached to them. And then I will take the loan agreements along with the units over to the bookstore, and then the bookstore will have them so that you can go there and physically pick them up. The school is not going to ship these to anyone, so you will physically have to show up to the bookstore and pick it up. Or if you can't, for whatever reason, after speaking with the department chair, he told me the only option if a student does not want to come to campus to the bookstore to borrow this is that they would have to purchase the MyDAC themselves. Okay, that's a $200 unit. Now, I think it's $200 well spent. I personally, as a student, would have purchased this because at the end of the day, that's more test equipment for me to get better at what I do and hone my craft and become a better engineer. And it is an incredibly useful piece of test gear. There's a lot more than just an oscilloscope and function generator built in. It can also behave like a multimeter. It can also partially act like a logic analyzer. There's a bunch of things. The bookstore... Where the heck is the bookstore? LMAO, feels like I haven't been on campus in years. The bookstore is right next to the like LA5. It's that upper campus. It's that place that none of us go to anymore. It's near like the Nugget and the 49er Nugget area where you can, I guess, get beer and eat food there. And then on the other side of the bookstore is the LA5, LA4, LA3 building. Yeah, the food area. Okay, where the beer is at. Oh, it's right next to that spot. Good. Okay. So, please download this file and fill it out. I'll go through this and then submit on Dropbox. If for the due date, no later than 10/18. That's this Monday. Fill this out today. Submit it on Dropbox. So that I can go ahead, because there's still a ton of work that I have to do. I have to organize the loan agreements. I have to make sure that everyone that has a loan agreement has a unit of the MyDAC waiting for them in the at the bookstore. So there's so much extra work that's gone on behind the scenes for this. So please fill out the student loan agreement, submit it on Dropbox, on Beachboard, under 311, no later than 10/18/20. So sorry, that's actually this Sunday, because I have to do all the work on Monday to get them into the bookstore, so that they will be ready, hopefully, by Wednesday. No, you don't have to print it out. Fill it out electronically, submit it on Beachboard. So it's in a document file. So with Microsoft Word, you can open that up and fill it out. Okay. So let's go over some of the responsibilities once you borrow this thing. Obviously, it needs to be returned in a good working condition, the same as when you got these. We will be testing them afterwards. The way this agreement is written is that if it is broken or damaged for any reason, then the student is obligated to replace the unit with another one. So that would be, you would have to spend your own money and buy one if you damage the department's MyDAC. Okay. So yes, during the loan period and prior to return, the borrower agrees to assume all responsibility for maintenance and repair of the equipment. The borrower is responsible for the full cost of repair or replacement of any or all the equipment that is damaged, lost, confiscated, or stolen from the time borrower assumes custody until it is returned to the department. Okay, what happens if you don't? Students who fail to return the equipment or fail to replace lost, stolen, or damaged equipment may get referred to the Office of Student Conduct and Ethical Development for disciplinary action, and or get a hold placed on their student account. A hold would not allow you to enroll in future classes. Okay. If the equipment is lost, stolen, or damaged, the borrower agrees to promptly notify the department representative designated below. So the department representative who's responsible for these is me. And my name's already been added and listed under here. Okay, the borrower agrees to use the equipment for academic and research use only and not for any commercial use or application. Of all the things on this list, this is the least that I'm concerned with. The borrower agrees not to lend the equipment or transfer this agreement and the responsibilities as outlined in the agreement to a third party without the written approval of the department. So you cannot loan this out to your neighbor. Okay, let me go through and see some of the questions from chat. Wait, do we have to print it to sign it? No, I believe electronically you can do a signature and add that as an image on the Microsoft document. Do we just put our initial for our signature? No, full signature. Just your name signed like any other legal contract. And we have to use this. Now that's a good question. As opposed to using what else?
I'm not sure. I mean, up till now, like you've done the labs, so I'm not sure what
Yeah,
else.
exactly. You guys have had it easy thus far. I've been doing all the labs here and broadcasting the labs. So okay, here's an alternative. If you don't want to use the NI MyDAC, and you don't want to buy the NI MyDAC, that's fine. At the end of the day, the NI MyDAC is replacing an oscilloscope and a function generator. That is what we're going to be using it for in this class. So if you have your own oscilloscope and you have your own function generator, those two are perfectly acceptable in lieu of the NI MyDAC. Okay, I'm using the NI MyDAC as because it is loaned out. I will use that for the remaining labs. I haven't gotten one of these units myself. I'm supposed to get one. I got permission to come to campus today, so I had to email the associate dean and ask for permission to go up to the office so that I could pick up 2 of these units. So I have not used one of these yet. I know what it's capable of. I've used other units that are very similar to it. So I have certain expectations, but I do not have one myself to experiment with yet. I have a ton of test gear. I use test equipment all day long at every single job I've ever been at. And I have my own home lab setup, as you guys have seen. So I am happy to support anyone that wants to have their own oscilloscope. I've given options on the website under the $100 electronics workbench. We already built a function generator. So that function generator would do exactly what we would need for this class. And I already went through that, and the video is posted on the $100 Workbench Challenge web page on my website. And the oscilloscope, there is a cheap $30 option that I think is worth it, and that's under that $100 Workbench Challenge page as well. That's the DSO-150, and it's about 30 bucks, 35 bucks. It does need a 9-volt external power supply to work, but that will do everything that we would want for this class as well as for future classes. So you're more than welcome to have your own test equipment, and I've done as much as I feasibly can to make test equipment as accessible to people. I'm using up my own time to do these electronic workshops. I've spent hundreds of dollars of my own money for testing out and seeing the capabilities of this low-cost test equipment. And for every one piece of test equipment that I recommend, I've purchased 3 or 4 other ones that I don't think are that worth it. So the accessibility is there. What I can't do is do the thing for you. Let me go ahead and look through some of these other messages. Is there a link on your site in case we decide to buy it instead? Ooh, good question. I hadn't thought about that. So, yes. Obviously, you can get this. Now, here's the place that I would recommend to get it from. Studica. If you go to the Studica website and you type in MyDAC, there is a student version. We can actually, our department cannot buy the student version, which is a shame because I actually preferred the student version. And let's see where it is. Okay, this is what I tried to get. Which was actually pretty cool because it came with all the components that we would want and breadboard and prototyping wires and this and that. It had everything we wanted. But unfortunately, this is only for students and the department was unable to buy this. But you can. Unfortunately, that one's $380. I wouldn't bother doing that. You have a lot of those components and breadboards and equipment already. I would get the NI MyDAC hardware only for students. So this is the link that I need to put on my website. So I will add a section. Purchasing MyDAC, add to website. So I will put that note for me and then I will add that after class. Awesome question. Okay. So you can get that. Do we have to fill anything out before we go to campus or do we just show up like a COVID test? No, you will have to fill out. I don't know if there's any type of process for the student to show up to campus. I believe you can just go to the bookstore. So once you've filled out the student loan agreement and submitted that on Beachboard by this Sunday, I will let everyone know when they are available in the bookstore. It should take about a week. We just need to label them and then put them over to the bookstore for every student that submitted a loan agreement. So if you don't get that loan agreement by Sunday, there won't be a unit waiting for you in Beachboard. There won't be a unit waiting for you at the bookstore. Oh, thank you, Alex. I wouldn't say I'm the best professor, but I can be beastly at times. If I buy it, can the school reimburse me? No, definitely not. The school is not going to pay for your lab test equipment, but they will loan one out for you provided you fill out the loan agreement and submit it on Dropbox by Sunday.
By this Sunday, we have to pick it up?
No, by this Sunday, you have to submit the loan agreement.
Oh, and we pick it up by next Sunday?
I will let you know when pickup is available. I will send out an email to everyone.
All right.
If I get one, will there be opportunities to use in your Friday benchtop demos? Yes. Okay. So at the end of the day, the NI My DAC is just a USB based oscilloscope. So you can use it for anything you can use an oscilloscope for. Now, when I do the oscilloscope workshop session, which will not be this Friday, but the following Friday, I will be doing the oscilloscope workshop where I compare a few different oscilloscope models that are very low cost, 30, 40, 50 bucks for a pocket oscilloscope. When I do that, there will be a couple of tests that I am doing. I will do a digital-based test, something like pulse width modulation coming from a microcontroller. And the other test that I will be doing is a purely analog-based test where we measure the rise time of an RC circuit, a simple resistor and capacitor circuit that I will use the function generator to apply the stimulus for the RC circuit. Just to let everyone know, let me switch over to the camera and kind of show you what that is, because that's both pieces of test equipment being used. So I think it's a good example of what you would use a function generator for and an oscilloscope. So what I will be doing, not this Friday, but the following Friday in my electronics workshop is with a simple RC circuit. There is a time constant associated with this, and I believe I covered this last semester in 211. I should have, where the time constant is equal to RC, and from the moment this cap starts charging, if we feed it in a square wave going into this circuit, the cap is not going to charge up instantly. It will take some time, and the time that it takes to fully charge up to 100% is 5 times the time constant. Okay, so one time constant takes you to 63.2% of our max value. So if we feed in a 5-volt square wave in here, it will take 5 times whatever these two values are in order to reach 100% of our max value, or 5 volts. I will be taking a measurement of this time constant using an oscilloscope to view the waveform, and the signal will be provided by the function generator. So function generator on the input and oscope on the output. So that's going to be my quote analog test for our pocket-based oscilloscope in the electronics workshop. And then the function generator will be the function generator we already made. Now the NI My DAC will be able to do both of these things. So it will act like the function generator and the oscilloscope. Okay, so kind of a cool piece of test equipment, but it's not the only one that's capable of doing this. There is another option, which is the analog discovery. The analog discovery also does the same thing. In fact, the analog discovery and the NI My DAC are essentially equivalent. Functionally, they do about the same thing. So you have options here, and you actually have low-cost options if you really don't want to come to class and get some free lab test equipment to be loaned out to you, let me list those options. And I will also add this to the website. So add to website. Link for MyDAC and other options. Okay, so you have the NI MyDAC. You can borrow from bookstore, or just purchase yourself. There's the analog discovery. There are two versions of this. There's 1 and 2. Either is fine and works great. And that's a piece of USB lab test equipment that actually can do quite a bit. Now, I'm familiar with the analog discovery because I've used it a bit more, but it has a function generator, it has a 2-channel oscilloscope, and it also has a lot of other kind of cool features. And the NI MyDAC seems to have the same kind of features. So either one of these are good options. But if you already have access to one of these, you can use that instead of the MyDAC. Okay, and your other option your own function generator, oscope, and benchtop power supply. So things that I've already covered, I already covered making a function generator, and I already covered making a benchtop power supply unit. Now, this is about half the price of an analog discovery or an NI MyDAC. However, this also requires a bit more effort on your part. So I've already done videos on that. And you're more than welcome to, do this as however you want. If you want to make the function generator that I built during the session and make the benchtop power supply that I built during the session and provide your own analog oscilloscope that you found on eBay, that's fine with me. You really have your own options to do however you want. Everyone has a different interest in this. If you don't want to, if you're not all that interested and all you want is a grade in the class, you can go ahead and borrow from the bookstore and then work with that. Or if you are interested in, something to carry around in your backpack, just like the NI MyDAC, and you have access to an analog discovery somehow, that's a great option too. I'll support all of them, and I will spend the time to help anyone outside of class to get experience with this type of equipment because I think it's that fundamental and that useful. Okay? So, let's see. We've eaten up, the entire class time here? Okay, but we did get a few more people. So, just to reiterate, please, by this Sunday, go to my website, download the equipment loan agreement, fill it out, change the file name to match your first name and last name, and then submit that on Beachboard Dropbox. And then everyone who wants that, I can have available in the bookstore, and then I will send out an email when they are available. Okay? And then we will use that for our next lab, which is the amplifier. So we will be constructing our own amplifier on our breadboard and then using the MyDAC for the first time on that project. Okay, so if there are any other questions, feel free to ask now or put them in chat. Otherwise, I'll get started on our normal class material.
Professor, is there a way to get the oscilloscope loaned out if you're like not in the area?
No, so and I that is a specific question that I asked the department chair, and he said the school has no plans on for shipping anything out to anyone. So physically going to the bookstore is the only way to get this unit.
Okay, gotcha.
To have it loaned out. So if there is, if you are in another state for any reason, then your options are to either come over here and either come over here physically or purchase it online or create your own home electronics lab. What's MK Day? How is the exam on MK Day going to be? Monday. Oh, okay. How is it going to be? It's going to be online. So it's going to be as a Beachboard quiz. Today is what day? Is today Wednesday? So is our exam on Monday?
Yeah.
Okay, now I'm seeing WK Day. No work turning in. Just kidding. Okay. So yeah, it's going to be the question and then a numerical response for most questions. And on the website there is some homework problems, there's all of the topics for the exam, and there's a practice exam that I've already given out. So this is exactly the type of exam. I actually really suck at making multiple choice questions, so I don't even bother trying. Yeah, I don't really do multiple choice. I've never had success trying to make them. So the example practice exam that's on here is very reflective of what you would see on this exam. The only addition, and it's on this Monday, right?
Yeah.
Okay, so yeah, it's going to be the base bias version of the transistor circuit. I will not be asking any questions related to new material from today. Okay, so it's just the transistor. And if you want some practice problems for this transistor circuit, if you go right above the practice exam is the transistor practice problems. You can go over here, and if you see, there's the load line analysis portion with the DC analysis portion, and you can do number 1 is good for practice, number 2 is good for practice, number 3 is great for practice, and number 4. Actually, all of these are, you got 5 practice problems plus lecture examples for this transistor. As far as the length of time for the exam, it will be 1 hour. Exactly 60 minutes. So I'll go ahead and give you my disclaimer that I gave my 211 class, which is that I highly doubt that anyone will finish every single problem from the exam. Okay? As how many questions? So it'll probably be about let's say 1 1/3 to 1 1/2 the length of the practice exam that is on there. So the practice exam has 18 questions, so expect about 20 to 23 questions. Okay, now I doubt that anyone will finish the exam by the time that the exam is up, and that's okay. I'm not expecting anyone to finish the exam. No, it's going to be 1 hour. Because when I make the exam, I have to put multiple questions for each question. So I create a question pool, and everyone, when they check into the online quiz on Beachboard, a randomly generated exam gets generated for them. So if I make the exam an hour and a half, then I have to end up adding even more questions, and it's already a daunting task to create 4 versions of every single question that I want to ask about for the exam. Okay, so here's the thing. Given that we were online, the worst thing about having these online exams is that half the class jumps onto Discord with each other, while the other half of the class does it by themselves. For whatever reason, you don't have as many friends in class, you're normally a shy person, you sort of keep to yourself. I don't want half of the class getting an 80%, getting a 90% on the exam, while the other half of the class ends up getting a 60% on the exam, just because they don't have as many friends and they're not on the in crowd on Discord. Okay? That's my biggest concern. And so that's why there is a time crunch with the questions for the exam. It's to level the playing field for the half of the class that is not as cool as the other half of the class. Okay? So if I make the exam such that it can be reasonably completed by most people within the amount of time, then that is super easy for everyone to just start giving out everyone's questions and answers on Discord. And I'm not accusing anyone. If I was in your shoes, I'd probably do that too if I could. But if I make the exam longer and harder than usual, or let's just say longer, then if I know that I can solve the answers and I've put in the time and practice, I'm probably not going to spend the time to help out other people when I can gain more points for my exam and do better. So at the end of the day, the scores end up being comparative, and the grade in the class ends up getting curved once at the end of the semester. Yeah, absolutely. So the whole class is curved. So I will be entering the grades as is into Beachboard, and then once at the end of the semester, everyone's grades get curved. So if the highest grade in the exam is 70%, that's fine, because at the end of the semester, I'm just gonna adjust those 3 or 4 highest grades in the class. Those are gonna be bumped up to a high A, like 95, 97%, and everyone's going to be curved and linearly adjusted to that grade anyways. You know, I used to say that. You don't have to outrun the bear, you just have to outrun the person next to you, right? I said that once in class and I got a couple of dirty looks, so I try not to say that too much anymore. Okay, so please understand that my goal with having a long exam is not to be mean. It's not to stress everyone out and to make this a very painful thing for everyone. It's to promote not cheating. That's really the end goal here. Okay? As far as everything else, it's open book, it's open notes, it's open calculator, it's open LT Spice running next to you. I can't control that. If you want to have a separate laptop and do Google searching for these questions, I can't control any of that. All I can do is reward the people that put in the practice for solving these problems. Because if you've practiced the problems from lecture and from the practice exam, and you can do those reasonably quickly, then you're going to do better than anyone else that's trying to input circuits into LT Spice to try and get the answer for the class, for the exam, right? So sorry, somebody had a question. What's up?
So are you gonna make us use Lockdown browser?
Yes. I will have Lockdown browser, and there will be a test Lockdown browser quiz that I will open up. So here's the thing. I've heard this in department meetings where somebody's like, where a very nice, naive faculty member will say, "Oh, use Lockdown browser. It's great because you can't cheat with it." Like, yeah, right. I can just take my cell phone and take a picture of the screen and send it to my friends. So Lockdown browser really doesn't, in my opinion, does not really solve the cheating problem. But here's what Lockdown browser does do. I had issues last semester when I didn't use Lockdown browser that due to certain plugins being in certain web browsers, I don't know, Chrome with ad block plus, or Firefox with download manager. I don't know what all the plugins are. But I did have problems where many people had issues in the middle of the exam where they couldn't see certain problems. Lockdown browser actually has its own browser built into it. So by requiring Lockdown browser, I actually I ensure consistency among seeing the exam. Okay, so I actually have less problems using Lockdown browser, and that's why I'm using it. Okay. But yes, I will have a test Lockdown browser quiz open so that you can verify that Lockdown browser works on your computer and your platform. Our exam will be from 8 to 9. to 9 a.m. No, I'm not gonna. There is no quiz. Sorry, I've been using the word quiz and exam interchangeably because Beachboard actually refers to it as a quiz. Oh, or maybe you're asking about the test quiz for Lockdown browser. Yeah, of course, that's going to go up today, right after class. I actually already have it created. I just have to enable it. Okay, are there any other questions about the format on the exam? Questions about the exam, questions about, time, stuff like that? Question about the MyDAC rental? I feel like today has just turned into a more of an administrative day. No. Yeah, don't worry about filling out serial number. I'll do that for you. Because the units actually don't have serial numbers yet. Will this be our only midterm? We will have a midterm and then we will have a final. So yes, this will be our only midterm. In the true sense of a midterm. Midterm.
Professor, realistically, how many questions do you expect us to finish?
I expect you to finish 15. Yeah, I expect about, let's say, 15 out of 23. I expect like about 2/3 of the exam to be completed by most people. Some people may actually get the entire thing. I don't know. But you can definitely expect questions that are very similar to that practice exam that's up there.
That's it.
Yeah, sorry, question?
Required to draw, right? Yeah, on the quiz.
I'm sorry, say that again?
We're not required to draw anything for the quiz, right?
No, exactly. That's one of the things I'm limited on. So here's how I would take the exam. I would have a bunch of scratch paper next to me, and as soon as the exam goes up, I would look at all questions from the exam before I even start solving any one of them. And I would get to the ones that I can solve as quickly as possible. So there's going to be questions that you see that you're like, I can solve this in 1 minute or 2 minutes. Go after those first. Get the low-hanging fruit out of the way. Once you have those questions, now look for your high-valued points that you know you can solve, but are going to take a little more time, but maybe worth, more points on the exam compared to the other ones. So things like 10 points, 15 points, get those out of the way. Then leave the ones that you're not too sure about till the end. Let's see, where's that feedback coming from? Yes, you will be able to see all questions. So when, yeah, I think, forgive me, Justin, I think it's coming from you because it's popping up your screen in the center of my Zoom feed. Yeah, thank you. Okay. So yeah, when you start the exam, the whole thing pops up as one long page, a sequence of different questions. They are randomized, so for each question there are 4 possible questions that could have been chosen, one of those for you. And then on top of that, they're all out of order and sequence. So it's a 2-time randomization that happens with the exam. Okay, so what else can I do for you guys today? Because I had planned to cover the BJT voltage divider bias. However, I don't think that's going to happen. So how about we just use remaining time for any type of review questions relevant to the exam. Since the exam is on Monday, I'll postpone the transistor lab again. It's not going to be that big of a deal. Normally during the semester, I actually have the lab sessions broken up in two sections. So actually, we've gotten through. We have time before the next lab, anyways. Wait, are we doing lab at all today? Okay, I'll take a vote. Who wants to do lab and who wants to do midterm review?
Review.
All right, cool. So go ahead and I'll do midterm review. I'll cover stuff from the midterm. So unless somebody asks me a question, what I'll do is I'll pull up the web page and I will go over those topics and just kind of list them out. Okay, so there's a section that says midterm 1 homework review and prep. As far as diode and rectifiers, there will definitely be, very similar to the practice exam. If you look at the last page, there are several different diode in AC circuits over here. So expect several different ones of these. And if you go to the AC analysis of diode circuit and download that page, you will see that I have listed every single form of this diode in AC. So you can see we have a series diode clipper at the top left. Then we have a series diode clipper to the right of it that the diode's been reversed. And then over here we have a shunt setup. And then we have a shunt setup where we turned the diode the other way. And then we have the same 4 but with Zener diodes. So you can definitely expect to see, 4 or 5 of these on there. And typically the things that I ask for is V out in peak to peak. So I could ask for actually, let me do this. Okay, so for any one of these diode circuits, I could ask for V out in peak to peak, or just for the peak voltage, or RMS. I could ask for V sub R. I could ask for V sub D. Okay. So for any one of those problems, I could ask for the value of V out, V sub R, or V sub D in peak to peak, peak voltage, or RMS. I will say most of the time I ask for it in peak to peak, usually. But definitely know how to convert all of these, because you could definitely see a problem where I ask for, for this problem, what is V out in RMS? And then you would go through your analysis, figure out what the peak to peak voltage is, and convert that to an RMS voltage. RMS is always equal to 0.707 times the peak voltage. Okay, so I think that probably takes care of those questions.
Professor, I have a question about are you gonna do like sort of like big circuit questions, like 211 questions on there, or just are we gonna
Yeah, so
focus
if you
more
look
on
at the
material?
practice exam, there is one that I did just to make sure that people have not forgotten that things in parallel have the same voltage across them, and things in series have the same current going through them, and resistors in series add, and resistors in parallel as the multiple over the sum. So yeah, there will be at least one of these types of 211 type questions. However, what I will not be asking for is I won't be asking for perform mesh analysis on this or perform nodal analysis on those. Those more elaborate analysis techniques from 211, I am not interested on for testing on that. I am more interested that just people have not forgotten Kirchhoff's current law, Kirchhoff's voltage law, those basic things. Okay.
I have a question. Are you gonna test us on like Y circuits?
On Y, like delta Ys?
Yeah, delta Ys.
Nope.
Cool.
Yeah, there will be no delta Y conversions on this exam.
Okay.
Okay. So let me go ahead. So that kind of takes care of the beginning part of the class where we talked a lot about diodes. There's also some other diode questions over here. Here's a question, in the following circuit, calculate the value of R given a desired diode current of 8 milliamps. Right? So I want 8 milliamps flowing through this, and I gave it that 8 milliamps going through D1 and through D2. Well, they're both in series, so they're going to have the same current no matter what. So this is a little redundant here. But nevertheless, just in case someone did forget that current is the same at every point in a series circuit. And then 22 volts applied, and the first diode, D1, has a forward voltage of 1.2 volts, and the second diode has a forward voltage of 2.4 volts. So you would take 22 volts, you would subtract 1.2 and 2.4 from them to account for these two diode drops, and now your remaining voltage is the voltage drop across R, and then you can set up your equation such that 22V divided by R equals 0.008 amps, and you can solve for what R is. Okay, so that's another type of diode question that I probably will ask. Here's another diode question. I did a lecture where I told everyone that this was one of those guaranteed problems that will be on the exam. In this case, it is a diode, a regular diode with a V sub F of 4 volts, which is a really large V sub F for a diode, but nevertheless, it could be a Schottky diode. Okay, and what I solved that day was a Schottky diode. We showed how we could use a Zener diode as a regulator, right? If I go ahead and do something like this. My voltage drop across the load is 3.3 volts because this Zener is going to always have 3.3 volts across it, so anything in parallel should have the same voltage drop across it. So you can use that as a regulator, and you can calculate all of the other parameters for this circuit. And you can see a good example of this right in the practice exam. Just switch out D1 for a Zener. Okay, so that's definitely the type of thing that you would see. Review linear power supplies. We spent a good amount of time on that. The half wave rectifier, the full wave bridge rectifier, adding that smoothing cap, how to calculate V ripple, fixed voltage regulators like our 7800 series, adjustable regulators like our LM317. We also looked at negative voltage regulators like the 7900 series, as well as the adjustable, well, actually, that will not be on the exam, the adjustable version of the negative regulator. But there could definitely be a question for an LM317. So if you go to over here, a good example of that type of question is this whole page right here. This is almost a guaranteed question on the exam. Okay, I don't think I've ever given a 311 exam where I did not have a power supply like this. So assuming that C1 is not present, what is V peak across the load? So if you didn't have this C1 over here and we had a voltage of 150 volts RMS applied and a 9-to-1 transformer, so you can take the 150 divided by 9, but of course that's in RMS, so we would want to convert that to peak. So you can divide 150 by 0.707 and that will get you the peak voltage. You can take that peak voltage, divide it by 9, that gets us the voltage applied to the full wave bridge rectifier, and then you lose 2 voltage drops, 2 forward voltage drops of our diodes for a full wave bridge rectifier. And for a 1N4001, we expect that to be about 0.7 volts per diode, so 2 diode drops would be 1.4 volts. So it'd be, 150 divided by 0.707, that whole thing divided by 9 for the transformer, and then minus 1.4 for the diode drops, and that would be the peak voltage applied to our load. Did I miss the class where we went over fuses? So, yeah, no question about here gives any information about that fuse. That is just a question, an image that I copied from a book somewhere, and it had the fuse in there. I've never had any issues with confusion where the fuse throws people off because there's no value associated with it. But no, we did not cover any fuses. Okay. So that gets us our peak voltage across the load. Calculate the value of C1 in order to give us a V ripple. So then you now use the frequency of your of the output from the full wave bridge rectifier. So if we have 80 hertz coming in, we know we're going to get double the frequency output from the full wave bridge rectifier. So that 80 hertz turns into 160 hertz, and then you plug that into the formula along with the peak voltage and the value of the capacitor to find out what V ripple is, and then you can solve for your capacitor that way. So that's kind of a plug and chug problem for B. What is the average DC voltage across RL given the previously calculated smoothing capacitor? So if you have, let's do this. When we have that smoothing capacitor in there, we expect if I have a lot of ripple, it's going to look like this. And I have some value V peak, and the V ripple is 800 millivolts. So that means peak to peak So if we wanted to know what the average DC voltage across the load given the previously calculated smoothing capacitor, well, that smoothing capacitor gives us an 800 millivolt ripple. So you can just half your ripple voltage. So that means our average DC voltage is going to be V peak minus 1/2 V ripple. So that takes care of number C, right? Our V ripple's 800, so you just go ahead and do whatever our peak voltage is, subtract from that 400 millivolts, and that's our average DC voltage. Assuming that in place of the load we connected an LM317, what is the largest regulated voltage that we could generate without dropping out of regulation? So this is a good question about the dropout voltage for a regulator. Now, I've always said that all of our regulators, let's take the dropout voltage to be 2.5 volts. So if I want to create 5 volts on the output, I probably should have switched over. I'm talking about this one right here. Assuming that in place of the load we connected a adjustable regulator, what is the largest voltage we could generate without dropping out of regulation? So if we wanted to generate 5 volts, we need to be 2.5 volts above the 5 volts. That's our dropout voltage. So this must be greater than 7.5 volts. Vn must be greater than that or equal to. What is the largest regulated voltage we could generate without dropping out of regulation? That's one of those good questions where you have to use that dropout voltage and look at what your largest voltage is that you can output from that regulator. So I will let everyone think about that one. In other words, I'm not going to solve that one for you right here. That one is great practice. And then draw the LM317. Obviously, I can't have you draw anything on the exam, but I could definitely ask you for the values of R1 and R2 to create an 8-volt regulator using an LM317. And so there's an equation to do that. It's that V reference, that equation that has Vref in it that's equal to 1.25 volts times the resistances. Okay, and then review basic linear circuits, a 211 type problem, no mesh nodal Thevenin. Somebody already asked me this. It was written right here. Okay, so a question that looks like this, or similar, a 211 type question, just looking that you remember your basic rules that we've been using, right? Kirchhoff's voltage law has been incredibly applicable this whole time. So is Kirchhoff's current law.
Professor?
Yep.
How would you write the last equation if it didn't have like if you were doing nodal analysis on it, if it didn't have a resistor?
Where? This one?
Yeah, assuming that you pick V1 right there to be your first point, and then where the R1 is your second, then R4 is your third, and then R6 is your fifth point. Voltage point, or whatever we call it.
Yeah, right. You want me to do nodal analysis on this right after I said no nodal analysis on this exam?
Nodal analysis is an easier way to do it. It's a faster way to do it.
Okay, so I am happy to answer that question after the midterm review, because I don't want to spend time on stuff that I'm not expecting people to do for this exam. Okay. If I eat up the next half hour on solving a hypothetical nodal analysis question, it's not going to benefit anyone.
Okay.
Okay, and then we get transistor, the BJT modes of operation. So saturation, linear, cutoff, your operating point, which remember your operating point is those three values, your IB, IC, and VCE. Power dissipation, I went over that on how to calculate. That there's lecture videos on that, and there's also the load line analysis. Okay, so let's see, today's Wednesday. Monday's video has not gone up yet. I will be sure to have those videos up by Friday at the latest. Okay, so today's Wednesday. Give me today, give me tomorrow, and Friday by midday is probably when I will be processing and uploading videos. Sure, load line analysis. For any given transistor circuit, I'll just make those the same. I'll make this be about, give me some numbers. 100K, 150K, 50K. Okay, 50K for that one. What about up here? 330, 400, 500, 1K, 200. Okay. So over here, we have a transistor that's being biased. This is known as a base bias. Circuit. I was going to elaborate on this today because the next circuit we will learn is the voltage divider bias. So the base bias looks like either of these two forms. These two forms are the same exact form. I just have the voltage that's being applied to the input of this resistor in series with the base. I just have it connected to the same voltage source as VCC in this version. Okay, so over here I kind of have it broken up. So we have everything we need in order to solve this. So let's go ahead and assume the linear mode. If we have the linear mode, then we can go ahead and calculate IB. IB is going to be equal to 12 volts minus 0.7 volts divided by 50K, which is equal to 12 minus 0.7 divided by 50K gives us 0.226 milliamps. Okay, now we can go ahead and calculate what our collector current is, assuming the linear mode. So we just take 100 times this, so we get 22.6 milliamps, right? Just beta times IB. Once we have the collector current, we can figure out VCE in order to determine if we are in linear or saturation. So by having a non-zero, non-negative base current, we already proved that we are not in cutoff. So we must solve further and get VCE to tell us if we are in saturation or linear. And calculating VCE, I needed to find IC first. And I found IC by doing beta times IB. Now we can go ahead and calculate VCE. VCE is going to be 12 volts minus the voltage drop of that 200 ohm resistor up here. And the current going through it is IC at 22.6 milliamps. So we can do 12 volts minus 22.6 milliamps times 200 ohms. That gives us 12 minus 0.0226. Yeah, it's 22.6 milliamps times 200 ohms. And we get, hey, look at that, 7.48, which means we're in linear. So these were good values we picked. At least for doing a load line analysis problem, because it's not in saturation, it's not in cutoff. Okay, so now we have our operating point. Our operating point is IC of 22.6 milliamps with a VCE of 7.48 volts, and we have a base current of 0.226 milliamps. Cool. Okay, now we can go ahead and do the load line analysis. We're going to do VCE in volts. We're going to do IC in milliamps. And we need to find our two endpoints. Okay, so we want to look at all operating points that this transistor could possibly be in. So you can imagine that you have a changing input to this transistor. You want to find out what are all possible modes of operation for this transistor. In other words, where could it be at any point? Okay, so to do that, we need to find IC at saturation, and we need to find VCE at cutoff. Down here defines our cutoff region. Over here along the y-axis defines our saturation region. So IC at saturation. Now, when we're doing the load line analysis, we take the saturation voltage to be 0 volts. So what is the collector current, assuming we have 0 volts between the collector and the emitter? Well, it's going to be the full 12 volts applied to this 200 ohm. So we do 12 volts divided by 200 ohms, just to apply Ohm's law. So what does that end up being? 12 divided by 200 gives us 60 milliamps. So that defines our collector current at saturation. Now we want to find our VCE at cutoff. Well, VCE at cutoff is just 12 volts because this is open. We have 0 current flowing through this, so we have 0 voltage drop across the 200, so we feel the full electromotive force of 12 volts applied to our collector and emitter. So we get 12 volts there. Draw a line. That is the straightest line I have ever drawn in my entire life. And now we need to go ahead and place our Q point along this load line. So this load line is all possible operating points that this transistor could be at given a changing input. But however, the way that this circuit is currently wired up, it is at a specific point along this line. And that specific point that is along this line is when we are at 7.48 volts with 22.6 milliamps. So let's go ahead and let's establish just kind of an idea of where we are in this load line. We're at 30 milliamps there. We're at 6 volts here. 7.48 is going to be in between these two, but closer to 6. So let's say right about there. And I'm just eyeballing it here. We should be a bit lower than 30 milliamps. Well, we are. We're at 22.6 milliamps. And this is our Q point. Very cool. Okay, so that's exactly how you do the load line analysis. Okay, any questions about this? So you got 4 different practice problems on the website. Okay, we also have, let's see, going back to the website. BJT, mode of operation, operating point, power dissipation, and load line. So that kind of covers all of that. There's some transistor practice problems here. There's a practice exam. Let's see. Let's run through the practice exam and see if there's anything that looks a bit odd. Okay, reverse breakdown voltage equals maximum reverse bias a diode can withstand. That is true. Avalanche current is the name given to the current that approaches infinite when a forward bias diode has no current limiting. No, avalanche current is actually when a diode is reverse biased and then it starts to conduct because it's breaking down. That's avalanche current. So number 2 is false. Number 1 is true. Silicon diodes are preferred for small signals. Okay, now think about that for a second. Silicon has a forward voltage of 0.7 volts. A signal diode made out of germanium has a forward voltage of about 0.3 volts. So if you want to not lose as much voltage from your signal, you would rather use a germanium signal diode for small signals, and it's implied in the name. So number 3 is absolutely false. A half-wave rectifier uses 2 diodes? Nope, it uses 1. That's a series diode clipper circuit is our half-wave rectifier. The depletion region in a diode decreases when a diode is forward biased. Yeah, absolutely. The depletion region, or the area between the P-N junction of your diode, shrinks when it is forward biased, and that's what allows the charge carriers to actually jump across. The typical forward voltage of germanium is 0.3 volts. For silicon, it's 0.7 volts. Okay, if our AC frequency is 2 kilohertz, what is the frequency of ripple for a half-wave rectifier? Frequency stays the same for a half-wave rectifier. So if you get 2 kilohertz going into a half-wave, you get out 2 kilohertz coming from a half-wave. A full wave, on the other hand, doubles the frequency. So if we have 1 kilohertz going in, what's F ripple for a full wave rectifier? It is 2 kilohertz. Okay, continuing on. To create an N-type material, how many valence electrons should the dopant have? Well, if I want to make a material that is more negative, it has an excess of electrons, so I want to dope the silicon with something that has more electrons. So if silicon has 4 valence electrons, I want to dope the silicon with something that has 5 valence electrons to get an N-type material. In the following circuit, we already covered that. We already talked about this one. Complete the schematic below. This is one of those questions that I would not have anyone draw anything for the exam. So I would probably give a half-wave rectifier, ask a few questions about it. And this brings in another point. I could ask questions about transformers. I could give you a step-down transformer or a step-up transformer, and give you an RMS voltage going into that transformer, and you give me a peak voltage coming out of that transformer, assuming either a step-down or a step-up with a turns ratio of 10-to-1 or 9-to-1 or 7-to-1 or 1-to-5. You know, all of those different options. I could definitely ask about voltages in and out of a transformer, and I could ask them in a way that requires you to perform some of those VRMS conversions to and from peak voltage, peak to peak voltage, that type of thing. We already talked about this kind of diode regulator circuit using a Zener. This one is drawn as just a regular diode, but I already gave the example with the Zener in there. We already did one of these where we did a base bias circuit and did the load line analysis for it as well. We talked about the power supply and the regulator stuff. And we talked about these, and there's plenty of practice problems. So any other questions that you guys have?
Are you gonna be available on Saturday in case we go through this and have a few questions?
That's a good question. I wouldn't count on Sunday for sure. You know, if
No,
I get
Saturday.
if I get questions on Sunday, you know, at 10 o'clock at night, I'm probably not going to respond to those. If I even see them. On Saturday, trying to think if I'm going anywhere on Saturday. Oh, I have a party to go to on Saturday, and I do. Wait a second, I'm not supposed to say things like that. This is COVID time. I am visiting a friend who may or may not be having a birthday, and I'm going to wear a mask, and I'm going to sit outside. Well, yeah, that's what I'm doing.
Okay.
No, actually it is, we did talk about that. It's going to be a very low-key friend gathering with 6 people total for a friend's birthday that we're going to do outside with some food. So when I say party, I mean old person party.
Literally like every party I attend to. You call me old.
What's up?
It's like every party I go to nowadays.
Yeah. What actually, you know what's devastated me more is the fires. I can't hike when there's fires going on in the mountains. Spray Lysol on the food. I'll kill the COVID and myself. Oh, and Saturday also I have something else that I'm doing in the morning. So there's possibility. Yeah, let me do this. I promise Friday after my 262 class and tomorrow, I guarantee that if you have a question that I will get back to you. On Saturday, I wouldn't count on it because there are quite a few things going on in my life. One thing I'm confused about is for the load line, why is... okay, great question. I mentioned this last time, but I probably did not emphasize it enough. Yeah, that's a fantastic question. Why, when I do the load line analysis, do I do 12 volts minus 0 as opposed to 12 volts minus 2? When the saturation model of the transistor calls for a 0.2 volt drop between the collector and emitter. Okay. Yeah, why are these two different? Okay. When we want to know how the transistor is behaving in saturation mode, you want to calculate IC as 12 volts minus 0.2 volts, because this transistor, we are trying to represent faithfully the behavior of the transistor. And transistors, like bipolar junction transistors, will have a 0.1 volt drop or a 0.2 volt drop or something within that area between the collector and emitter. So you can kind of think about 0.2 volts as being the worst case saturation voltage. However, when you do load line analysis, we want to know as extreme as it possibly could get, as saturated as it possibly could be, as closed of a switch as it possibly could be. And an ideal switch has a 0 volt drop across it when it is closed. A perfect transistor that is 100% saturated, as saturated as it possibly could ever be in this world, would have a 0 volt drop across it. So we want to know as extreme of saturation as possible. This is kind of worst case saturation, where it has a 0.2 volt drop across it. This is best case saturation voltage. Now, why these subjective terms of worst case and best case? Because I am equating this transistor to a switch. Open switch, best case switch, bad switch, bad closed switch. So our best case switch would have 0 volts across it because it's just a wire. and we have 0 volts between any 2 points along an ideal wire. A poorly closed switch, or a bad switch, a bad connection. If I have 2 wires that are kind of close together, but they're not really a very good connection, I'm going to get something other than 0 volts between it. I'm going to get like 0.2 volts. And an open switch, I should have all voltage across it. Okay, so in the case of load line analysis, where we're really trying to see these extremes in IC and VCE, we want to treat this like an ideal switch, as saturated, as closed as possible. Okay? Whereas when we want to describe the behavior of the transistor, we want to use a more accurate representation of that number. But yeah, that's an awesome question. Does that make sense? Cool. Good. When we do the transistor as a switch lab, you will see... I assume you mean move the board up. Okay. Yeah, when we do the transistor as a switch lab, which we will do not the day of the midterm, we will do it on Wednesday. So I will change the due date yet again. You will see that our saturation voltage is actually a bit better than 0.2 volts. It's more like 0.1 volts. But we got to have some fixed values. It's just like that forward voltage for a diode. We take it to be 0.7 volts, but you saw that it's 0.5 volts sometimes, and other times it's 0.6 volts, and other times it's 0.75 volts, right? How would you set up a problem where you have to find VD or V sub R for a diode? So I would set it up just like the practice example exam that I have. So like over here, here's a great example. Assume D1 is a 1N4001. What does the part of the sentence means? It means you got a 0.7 volt drop across that diode when it's forward biased. And V sub S is equal to 8 volts RMS. Well, that's the AC voltage that's being applied. Now, that's not a peak voltage. That's a root mean square voltage. So you're going to have to take the root mean square voltage and divide that by 0.707 to find out the peak voltage. Then you can go ahead and you can look at your two cases. What happens during the positive alternation? What happens during the negative alternation? And then you can go ahead and draw two waveforms and figure out where your V out and V sub S is equal to. So I'll solve one of these.
Damn it.
Why not? Let's go ahead and let's set up the same exact problem. What is it? 8 volts RMS? The R value doesn't matter, and this has a V sub F equal to 0.7 volts. Okay. Cool. So let's go ahead and let's start with what is being applied to this circuit. Okay. Some AC. What's the peak voltage? I don't know. This is given in RMS, so we need to convert this to peak voltage. So I would do A volts divided by 0.707 equals a peak voltage of 11.32. Okay, so this 8 volt RMS is behaving like 11.32 volts peak. So that's our highest. Also means that it goes down to minus 11.32. Now we want to ask ourselves, what does this diode do during the positive alternation? During the positive alternation, or when all applied voltage is going in this direction, it looks like this diode's reverse bias, so it's going to behave like an open switch. Okay, so that means, what is V out? V out is going to be, well, we have zero current flowing through here. We have 0 volt dropped across this resistor. And we're measuring V out with respect to ground over here, so the voltage drop across here should be whatever voltage is applied. Okay, that's kind of cool. Now what happens during the negative alternation? Well, during the negative alternation, current's going in this direction. Our diode's forward bias, so it will conduct. And when it conducts, we get a 0.7 volt drop across it. And all remaining voltage gets dropped across here. So let's give ourselves a couple of different values to look at. So 11.32 volts peak. When we have, when we have below 0.7 volts, so if we had 0.1 volts applied, what would we get for our output? Well, this diode would not be conducting at that point. We need to exceed the forward voltage, so the switch is going to remain open. If it remains open, whatever voltage is applied is what we get on the output. So for 0.1 volts in, we get 0.1 volts out. If we apply 0.4 volts in, we get 0.4 volts out. Until we exceed 0.7 volts, we actually don't get this diode to conduct. Once we hit above 0.7 volts, let's say 1 volt, now it looks like we get a 0.7 volt drop across this, and this is conducting. So 1 volt, we get 0.7 volt, and so forth. In fact, whatever voltage we have applied, all the way up to 11.32, when this is forward biased, we're going to always get that 0.7 volt drop across it. So it looks like we are going to follow this waveform until we hit 0.7 volts. At that point, we get a constant 0.7 volts across it. And then as we get below this 0.7 volts, now the diode begins to not conduct again. So we follow perfectly, and the cycle repeats. Okay, so it looks like 0.7 volts down here, 11.32 volts. So what is V out in peak to peak voltage? Equals 11.32 plus 0.7 for your peak to peak voltage. So it looks like 12.02 volts peak to peak. Okay, so that's exactly, and in fact, I think this is the hardest problem on this exam that I gave this specific year. So yeah, that's a good one. Okay, and then like I said, you have all possible combinations in that other diode sheet that I had.
Wait, Professor, why is it negative 0.7? Shouldn't it not allow any current? Like the diode?
Why is it so? It sounds like there's two things in what you said. Why is it negative 0.7? It's because it's below the 0 axis over here, right? So our applied signal goes as much positive as it does negative. So that's where the negative sign comes from. It comes from the fact that this AC voltage is going both positive and negative. But I think the second part of your question was...
Yeah, it was like, why is there 0.7 going through the diode if it's reverse biased?
So there's no 0.7 going through the diode. There is 0.7 volts across the diode. But the current that's flowing through the diode is greater than 0. We have current flowing through it because it is conducting. So if you notice our applied voltage is still going up. We are applying up to 11.32 volts. With this diode, and the diode is forward biased, so it is conducting, but all remaining voltage is getting dropped across the resistor. Only 0.7 volts is across the diode. But I like your question. If I want to keep on elaborating on it with you.
I mean, isn't a diode only supposed to have like the 0.7 volt drop if it's forward biased?
It is. Is it forward? Okay, so let me break this down. Is the diode forward biased during this period of time?
No.
All right. So during the positive alternation, are we not applying the current in this direction during the positive alternation? Current's going clockwise, right? And this is reverse biased. But when we hit the negative alternation, isn't our polarity now flipped from the AC voltage source? Isn't this true during the negative alternation? And now current is going in the opposite direction? And isn't that arrow going in the same direction as the diode? So isn't the diode forward biased during this period of time?
Yeah, it is.
Yeah, right?
Mm-hmm. Yeah.
Okay. And so when it's forward biased, as long as we exceed 0.7 volts, this will behave like a closed switch, right?
Yeah.
And if it's behaving like a closed switch with a 0.7 volt drop across it, then if I'm looking at the voltage across the diode, don't I always see 0.7 volts?
Yeah. No, yeah. So I was confused about like what the red was. I thought it was the like voltage across the diode, not like V out. Yeah.
V out is the voltage across the diode.
Wait.
V sub D is the voltage drop across the diode, right?
Yeah.
Isn't V out the voltage drop across the diode?
Yeah.
Yeah, right?
Uh-huh.
Yeah, exactly.
Okay. Thanks, Professor.
Yeah, of course. Okay, I'm rereading that question. How would you set up a problem where you have to find V sub D or V sub R for the diode in AC circuits? Okay, I'm thinking about that question a little more, especially now that the other person asked that question. So keep in mind, sometimes V sub D equals V sub out or V out. So if the diode, in fact, let me go ahead and pull up the all right, help me out with this one. What is V out equal to? V sub R or V sub D? V sub R, right? V out is the voltage drop across this resistor. It's not the voltage drop across the diode, because when we say the voltage drop at a point, it is reference to our ground. Okay, so V out is equal to V sub R in this problem. V sub D is a completely different story. That's the voltage drop across the diode. Okay, let's look at this one down here. Is V out equal to V sub R in this problem? No way. V out is equal to V sub D. V out is the voltage at this point. Ground is over on this side of the diode. Our 0 volts is here. And V out, our voltage at this point, is in reference to our 0 volt. So V out is the voltage drop across the diode in this case. So V out is equal to V sub D. Let's go this one over here. V out is equal to V sub R, right? Because it's the voltage drop across the resistor in this case. So you can think of this as having an input and an output. Now, I will always have the ground reference to signify what 0 volts is. That I have to have in here. And it's in the practice exam too. So in fact, this is how I phrase the problem. And you can see I have ground here and I have 2 points. So over here, V out is the voltage between this point and this point. It's a little more explicit because I put 2 terminals here. But over here, you can clearly see V out. Is it the voltage drop across the diode or the voltage drop across the resistor? It's the voltage drop across the diode, right? This one up here, same thing. V out equals V sub D. Over here, V out equals V sub R. Okay, so hopefully that helps. Feel free to ask further questions in chat.
So could you do a full wave bridge rectifier? An example of like how to do a problem with one of those?
Yeah, I guess. I don't know what you want me to do with a full problem for a full wave bridge rectifier.
Just like how you would go about setting up a problem for a full, like you don't have to do the whole thing.
Ah, 1N4001. All right, what voltage do you want coming in?
Let's do 120.
RMS or peak? Or peak to peak?
RMS.
So inventive. That's the same thing that comes out of my wall.
Hey, mine too.
You must live in the States. Okay, so we agree that this is 170 volts peak. Just take that, divide that by 0.707 and round it. You'll get 170 volts peak. Okay, and then we have 4 1N4001s, right? That's a really high voltage for straight into a full wave bridge rectifier. I'm pretty sure that that full wave bridge rectifier is going to go up in smoke. Let me check something out. One N4001. Let's see. Yeah, that thing's gonna pop pretty quickly. If it's a 1N4001. We could do it, however, if we use a 1N4004 or a 1N4003. I guess it can be done. Just have to make sure to use the correct diode for that. Let's do a 1N4004. It's still the same forward voltage, 0.7. Changes nothing. It just means that my paper will not catch fire when I try to apply my fictitious 120 volts RMS to this. Okay, so we have 170 volts peak going in. What do we have coming out of it? One 60, let's see, 168.6 volts. What was the frequency of our 120 volts RMS? Let's just say 50 hertz. I mean, so this is really all we can say about it, right? Step up transformer for extra fun. Right before yeah, it would have to be before the rectifier because the transformer is not going to work after the rectifier. But yes, step up transformer for extra fun, especially those, if you find an old microwave, take the coil out of there. You'll have plenty of voltage to play with. And by fun, you mean, well, hurting yourself. So that, I mean, this is really all we have to say about a full wave bridge rectifier, which is you get double the frequency on the output with 1.4 minus the volts of the input, right? But we did lose. The nice thing is we lost the negative portion of our waveform. So it's all positive. It's pulsating DC. It's at a higher frequency, so it'll let us use a smaller capacitor for calculating V ripple. So there's a lot of good things about this circuit. This is kind of the rectifier of choice. if you want the whole analysis of what happens during the positive and the negative alternation, I'd say go check out the video when I lectured on that, because I take a lot more time. I'm not going to do I don't want to do a 30-minute lecture on the analysis looking at the positive alternation, the negative alternation, which diodes are conducting during the positive and the negative, when I already have those on video in the previous lecture. And I took my time for doing that. But, very simply looking at the input versus the output, you get double the frequency and you have 2 diode drops. So instead of 170 volts peak on the output, our pulsating DC is 168.4, so minus 2 voltage drops of your diode. And let's see, what else can I say about this? This is pulsating DC. So the nice thing is any load that we connect here has the current only going in one direction. It never goes minus. So the direction of current is always down through this load resistor. I feel like we should just watch the Electro Boom full wave bridge rectifier video again. Okay, so I'll go ahead and I'll call it there. I will try to get the videos up. I'll try to get them up as soon as possible, maybe even later today for yesterday and today's video. I'll try my hardest to get those up today and Monday's video on the website. And you guys can ask me questions anytime. And I'll try to get back to everyone as soon as possible. And if you need office hours, just go ahead and email me, let me know. And I'm happy to open up Zoom. And aside from that, I will see you guys on Monday. Okay? Take care, everyone.